One particularly important result that's useful for computing limits is called the squeeze theorem. Roughly, what this theorem says is that if f is a function that's trapped between two other functions, say g and h, both of which tend to the same limit as x goes to a, then f must tend to that limit too. The picture is convincing enough to be a proof. After all, if g and h have the same limit, then their graphs must converge to a single value, say L, and if f is trapped between the two, then its limit must be forced into this single value as well. Precisely, the statement reads as follows. Assume that the functions f, g, and h satisfy the string of inequalities g is less than or equal to f, which is less than or equal to h, for all values x near a, except possibly at a. If the limit as x approaches a of g of x equals L, and the limit of h of x equals L, then the limit of f of x must be equal to L too. The utility of this result is that it's another tool to wield, for example, in those situations where algebraic manipulation appears to be fruitless. For example, consider the function f of x equals x squared cosine of 1 over x, which we'd like to take the limit of as x goes to 0. We've already seen how to graph the factor cosine of 1 over x, which has an amplitude of 1 and an infinite number of oscillations as x goes to 0. The limit of this particular factor does not exist, but f of x has an extra factor of x squared out in front, which changes the amplitude, and which could possibly change the nature of the limit. In fact, the factor of x squared implies that the graph of f should look like the graph of cosine of 1 over x, except that it now has an amplitude that changes in x, an amplitude which behaves as the function x squared. This means that if we draw the curves of y equals x squared and y equals minus x squared, then the graph of f oscillates between these two curves, touching them at the points where x is the reciprocal of an integer multiple of pi. From this picture, it's clear that we're in the situation where we can apply the squeeze theorem. Indeed, we can let the lower function g of x be minus x squared, and the upper function h of x be x squared. With these conventions, then, the graph implies that we have the string of inequalities g is less than or equal to f, which is less than or equal to h. Now, we're interested in the limit as x goes to 0, and for g and h, this limit is easy to compute, it's just 0. Since these functions share a common limit then, the squeeze theorem implies that the limit of f must also be this common value, namely 0. Now, the approach we just described arrives at the string of inequalities through a geometric argument, but it's probably easier to arrive at this string of inequalities through a purely algebraic argument. In particular, the function cosine is always trapped between minus 1 and 1, which implies that we certainly have the string of inequalities minus 1 is less than or equal to cosine of 1 over x, which is less than or equal to 1 for all x where this is defined. Then, to get a string of inequalities involving f of x, we should multiply everything by x squared, and then f of x appears in the middle. Also, the inequalities do not change direction when multiplying by x squared because x squared is a positive number. What we obtain then is the same string of inequalities we saw before. An important point which should not be overlooked, though, is that we could multiply by x squared without changing the inequality signs. This isn't always the case. For example, consider the function f of x equals x times sine of 1 over x. We could again start with the inequalities, saying that sine of 1 over x is trapped between minus 1 and 1. But now, if we try to multiply this string of inequalities by x, we realize that we don't know which direction the inequality sign should point. When x is positive, then the directions are preserved, but when x is negative, then the directions are reversed. Because of this, it's more difficult to find the functions g and h which trap f. A common trick, then, is to try to trap the absolute value of f by two functions instead. The absolute value of f is easier to trap because its sign is always non-negative. In terms of an algebraic argument, we can start with the absolute value of sine of 1 over x, noting that it's trapped between 0 and 1. Then we can multiply this string by the absolute value of x, and the direction of the inequality signs will be preserved because the absolute value of x is always positive. What we obtain then is that the absolute value of f is trapped between 0 and the absolute value of x. Thinking of the constant 0 function as the function g of x, and the absolute value of x as h of x, then we could try to apply the squeeze theorem to this string of inequalities. Since the limits of g and h are both 0 as x goes to 0, the squeeze theorem implies that the limit of the inside function must be 0 too. In this case, the inside function is the absolute value of f, so the squeeze theorem implies that the limit of the absolute value of f is 0. At this point, we're not quite done with our problem though, because our objective was to say something about the limit of f, not the limit of the absolute value of f. Nevertheless, there's really only one more observation left. The observation is this: the only way the absolute value of a quantity can be 0 is if the quantity is 0 itself. This means that we can conclude that the limit of f is 0 as well, and we're done. Geometrically, the function f has an amplitude that behaves as the function x, which means that its graph is trapped between the lines y equals x and y equals minus x. From this picture, it's clear that we could have bounded f by the functions minus absolute value of x and the absolute value of x, and applied the squeeze theorem to this string instead.